Welcome to the final sidebar of 2024. Thank you for coming, and thank you to Dr. James Wingham for stepping in. Many of you have already been up and seen his wonderful 3D printer and all the things that it can make. But tonight he's going to talk to us about 3D printing and what it may be able to do in the future. So thank you, James, and over to you.
Okay. Got to get my microphone sorted out. Cool. So thanks for having me along. I'm James. I work at Manchester Metropolitan University. I'm a lecturer in engineering there. My research is all around 3D printing. So I'm on sort of materials for things and different areas with like antimicrobial materials. But that's not what I'm going to talk about tonight. I'm going to sort of go with more general introduction to what 3D printing is. So hopefully this is going to work. There we go. So there we go. A little bit about me. I won't spend too long on this. So I say I'm a lecturer in engineering. I started writing out what I'm actually, and it just took up too much space. So my background is mechanical engineering. My research is more in material science and microbiology. And I currently teach on the product design engineering course and every other engineering course that we do at ManMet, including the one in China. So, right. But that didn't really fit on, so I just put engineering. So my research is all around polymer laser sintering. Don't worry if you've no idea what that is. I'll get onto it in a minute. So that's my sort of area, additive manufacturing, 3D printing, more on the material side. So lots of material characterization, different functionalities, things like that. And I really like working on multidisciplinary projects. So working with people that don't usually work together. So microbiologists and engineers and things like that. So 3D printing, it's all brand new, right? Does anyone want to have a guess at when the first 3D printer, as we would recognize it now, came around? How long do we think it's been around? So was that 99? Okay, any advances on 1982? Well, it's somewhere in between there. It is 86. So the first 3D printer that we would recognize was around in 1986. This type of printer has been around, well, it's patented in 1988. But I think the reason that most of us think it's brand new is it only really hit the media, I'm going to say in about 2008. And there's a link there because that's 20 years after it was first patented. So when the first patent ran out and it stopped being this £100,000 plus machine, and people thought, actually, I can make this for £100 and sell it to people, it suddenly exploded. 3D printing was everywhere. It was all over the media, all of these claims of what we could make, what we couldn't make. So most of us, when we think about it, think, oh yeah, late 2010s maybe is when it came around. But actually, lots of this has been around for 30 plus years. So I thought I'd start with a bit of a definition. This is contested. It's not the only definition of 3D printing. But so 3D printing is a process of joining materials from 3D model data, usually layer by layer to make parts, different from subtractive and formative manufacturing. So that's sort of the ASTM standard for everything. You can tell by that, it's not a very restrictive definition. It does include machines like this, but there are also hundreds of different processes which also fit in this and are also 3D printing. I should at this point also say, if I switch between 3D printing, additive manufacturing, AM, it's all the same thing. Additive manufacturing is the more technical term for it. It now basically means the same thing as 3D printing. It's had lots of different names over the years. Solid fabrication, freeform fabrication, digital manufacturing, rapid prototyping. Generally, we stick to additive manufacturing or 3D printing for now. So I said there's lots of different types. Generally speaking, and this is very generally, most of them follow the same sort of general process. So all 3D prints start from a CAD model. So a 3D model that someone makes on the computer. If you really are interested in this sort of thing, you need to make it into an STL file, which is basically just a surface geometry of whatever you make. And then between that and sending it to the printer, you need to slice it. So I say it makes everything layer by layer. So you need to figure out what those layers need to be. So different printers, some might be more complex than others, but generally speaking, you split it up into a stack of slices so you can tell the printer instructions on what to print. Then you've got all the things to do with the machine itself. Have you got the right materials? Have you got the right parameters? Have you thought about where it's going to be in the build chamber? Can you print more than one thing at once? Is it the right orientation? All of those sort of things, which is all dependent on the machine itself. But there is generally some sort of messing around with settings so you can actually get it set up ready to print. So it prints in whatever form that is, and then you can end up with your print. But there are extra things. There's usually quite a lot of post-processing and things that go in. So some things require support materials, which you have to sort of break off and remove. Some things have loads of powder in, which you need to get rid of. Some things are encased in a block of uncured resin, which you have to sort of chisel off. So some sort of process to end up with your final parts, which you can then go and use. But this is sort of the general method of 3D printing in most cases. Cool. So there are lots of different types of printing. I'm just going to go through 3 examples of specific types of 3D printing, just to give you an idea of what this actually looks like. And I'll come back and talk about applications later on, but just for a few different examples. The one that you've probably seen, partially because it's here and running, feel free to come and have a look later on and have a chat about it, is FDM, so fused deposition modeling, in the category of material extrusion machines. So the way these ones work is you've got a nice filament here, which is a solid material. It's fed into a really hot nozzle. It melts in the nozzle and only in the nozzle. Then basically, as soon as it comes out the other end, it solidifies and you can make layers up that way. So think about like piping icing onto a cake or squeezing toothpaste out of a tube, that sort of way. It's good for some things. It's good for things like this because it's really quite portable now. It's quite cheap. You can get a quick idea of what geometries look like. You can make sort of simple assemblies and things like that. Maybe some slightly more complex ones with some sort of basic materials. But this sort of printing is relatively limited. It's not that precise. The mechanical properties are okay, but they're not great, especially on these sort of printers. The expensive printers, which do still exist, sort of £100,000 plus ones, that can print really high temperature materials, they can still be really good mechanical properties. So things like PEEK materials like that, which sort of compete with metals for like aircraft applications and things like that. But generally speaking, this sort of technology is great for showing off 3D printing, but that's really where it sort of stops and sort of initial prototypes of things. Some people will argue with me about that later, but that's what I'm going to go with. So that's one type. Another one which you may have seen is stereolithography, or the resin printers of various descriptions. So this was actually the first one to come on. That doesn't really show very well on that screen. So this was actually the very first 3D printing method that was developed. So this works where you have a vat of resin and you have a laser to cure the resin where you want the part to be. So once you've cured that layer, spread another thin layer of resin over the top, cure it again, and at the end, sort of push out all of your parts, get rid of, wash off all the uncured resin, maybe you do some post-processing to cure everything that's left, but that's how you're left with those parts from that initial resin. So this is probably, for most people, the next step up from the FDM sort of printers, because they are a bit more expensive, and there are more health and safety risks with resins and things like that, but you can get much finer resolution. So these are really good for small, detailed products. So I don't know if we've got any sort of RPG gamers in here. Anyone do Warhammer or anything like that? Oh, that's more than I expected in the room. So you might be already familiar with processes like that. So it's really good at making those small, intricate models that you can then spend as long painting afterwards as you do printing them out. You can also use it for different things. So there's a pair of glasses on the end. I'll come back to this a bit later. But so jewelers use this sort of process as well, not to make the final products, but as to make like the patterns for it. So think about investment casting or lost wax casting, that sort of process. You can print the patterns with this, and then you can make the mold around it, burn it out, and then you can use conventional materials like silver, gold, whatever you want to use to make your jewelry. So that's sort of the next step up from the sort of basic ones. The next one that I want to go over, which is, again, probably more used than lots of other processes, is laser sintering. Now, you'll have to indulge me a bit in today's talk. This is my area, so I've got a disproportionate number of examples, things from laser sintering, and I'll probably talk about it a bit longer. But this is a process you might not have heard of. So this is a powder-based process. So it works by spreading a thin layer of powder this time rather than resin, melting it with a laser where you want the part to be, spreading a thin layer of powder over the top, melting it again, and at the end, fish out the parts, brush off the powder, and that's what you're left with. There is a really wide range of materials that you can process with this in theory. Practice is slightly different. In theory, anything you can melt with a laser, you could process in this with this process. So all of my stuff is based on polymers, and they're sort of engineering grade polymers. So all the bits I've got here are sort of nylon 12 and sort of actually really rigid and fit for purpose. Large application with all of this is also with metals. So it gets a lot more expensive with that, but you can make really strong metal parts with really intricate geometries using processes like this. Especially for metals, you can get a really high level of control over the microstructure as well. So you can have custom microstructure in different parts of your process, which you can't get conventionally anyway. And it's really good for things like lightweighting and all the rest of it. So I sort of go into a bit more detail on this. So you can actually see what it looks like. This is inside one of the laser sintering machines. You can see the laser was there scanning all of those different bits. So it's melted it where it wants the parts to be. Build bed goes down, new layer of powder over the top, and the whole thing repeats. Sped it up slightly for this, but you get the idea. Actually, that's a lie. I haven't sped it up. I've just cut it to the bit which is really useful. There's a bit like 20 seconds where temperatures come up, but the actual scanning is that quick. So you can make lots of parts in the same way. And things like polymer laser sintering, you don't need any supports. So you can print things on top of each other. You can print hundreds of different things in the same build and sort of scale up very quickly that way as well. A little bit of post-processing. So you take it out of the powder, so you get this nice powder cake here. You get some nice powdery parts, and then you can sort of brush them down, use like an air jet or something to get rid of all the loose powder, and you're left with your parts on the right there. So that's 3 specific types of 3D printing. Like I say, there are lots and lots more. ASTM tried to make, or has sort of successfully made categories for these. So FDM is a material extrusion process. Stereolithography, the resin one, is a vat photopolymerization process. Laser sintering is a powder bed fusion process. But there are also lots more processes which are fundamentally different to each other and work in different ways. I'm not going to go through all of them, but if anyone is interested, feel free to have a chat with me and I'll talk through all. But it's just being aware that each of these categories with lots of different processes in them, even on the ones I've already said about. Okay, so why would you use 3D printing? What's it good for? So I've tried to summarize bits and sort of condense it. A couple of wordy slides, but hopefully it gets the message across. So because you don't need tooling for each individual part that you make, there are lots of benefits that come with that. We can make really complex geometries that you couldn't, for example, with, say, injection molding, where you need to think about things like draft angles and parting lines. We've got far fewer restrictions than things like that. You still have restrictions, but not as many. Because we don't have to make molds and things like that, we've got generally shorter lead times. We don't need to wait 6 months and spend £500,000 on an injection mold. We can just make it pretty much straight away. And one of the big things is we can change what we make sort of every single print. Other than the design cost, from the printing side, there's no difference of printing 1,000 identical things to 1,000 completely different things. And that's really good if we're trying to do like mass customization, personalization. You may have seen things like the American company Invisalign for like custom dentures and things like that. All of those are 3D printed, and they're all obviously completely different. And that's the way that they do them, and really good use of 3D printing. Sort of on that level, but thinking a bit more industrial, if you had a factory, obviously 3D printers can make different parts without needing to stop and have downtime for changing over tools or changing over processes. So it can be much more agile. We don't need to have a huge warehouse full of things. So we don't need a warehouse full of spare parts because we can just print off a spare part. We just need the file to start with and we can make new ones. We can also consolidate parts. So rather than having lots of complicated parts which are bolted together, we think, okay, let's make one more complicated part, but just as one thing. I'll give examples of that a bit later on as well. And then there's the sustainability side of things. Now, this is somewhat contentious sometimes. I'm not going to stand here and say all 3D printing is more sustainable than conventional methods, because it's very much a case of it depends. But generally, we have less waste material. So conventionally, for if you're machining a block of aluminium to go on an airplane, it's something like 5% of that block that actually makes it up there. So all the rest of it is chips that needs to be recycled or dealt with somehow. So we've got much less waste because we can process it and we only put material where we want it. Lightweighting parts can make a huge difference. So we can make really complex geometries that are shaped they need to be rather than the shape they have to be because of the process. And if you think about components on an airplane, then even if it's a few grams saved up there, that could be hundreds of tons of fuel over the life of the plane. So it's thinking over the whole life cycle. And sort of local manufacturing as well. If I'm collaborating with someone in Australia, I don't need to make them a part and ship it to them. I can just email them the file and they can print it there. So it makes it a lot easier to do things like that. I'm not going to try and brainwash you for additive manufacturing and say it's perfect. So I will go through the disadvantages of all of this as well. So cost is quite a big one, especially capital cost at the beginning. When you're talking about setting up big metal machines, you're talking sort of millions of pounds sort of level, which can put off a few people. And the materials are also a bit more expensive as well. But that is coming down. Especially as there's more competition, they're getting much more reasonable. The speed of prints is generally quite good. The downside with this is when you're trying to scale up, because the time it takes to print one part generally is the same per part as if you're printing one or printing 10,000. Whereas, say, injection molding, when you want to scale it up, you can make things a lot quicker by using different processes. So there is a cutoff sort of below which 3D printing is great, above which you probably want to go to other methods. This is an interesting one, a sort of part properties, the quality assurance side. This is getting a lot better, but it's just drawing attention to there are lots of different processes, right? Lots of different materials within that. So if you're trying to set up standards and things for people to follow, they need to be insanely specific. Now, there are some insanely specific standards out there now, but they're few and far between. So making sure that power quality is the same between different printers, different groups, different countries, it's more of a challenge than with other methods. Whole arguments with intellectual property get a lot more complicated. We've got who designed it, who printed it, who made the file, who sliced it, who printed it, probably not. The person who signed it off at the end, the person who bought it. Lots of people there. And when it gets to, say, controversial topics, like the one that's been in the news a lot recently, 3D printed guns, if something happens, the question of who is to blame doesn't have a simple answer. I think Joe Biden even set up a US task force specifically against 3D printed guns this year, I think. I'm seeing some nods. So this is a problem which exists and is a lot more complicated with processes like this. And sort of the big one is people are saying, I've been using this process for 50 years. Why should I change it to your new process, which is expensive and have all these problems? That is a real issue that we're sort of slowly overcoming, but we do still encounter quite a lot of resistance, especially in companies that have been using the same methods for a long time. We're not trying to replace everything, but just give an alternative or different ways of doing things. And for all of our students, our graduates, we equip them with these skills to know both methods, so traditional methods and 3D printing methods, so they can be better informed going into industry with all of their partners, things like that. Okay, I'm aware that was lots of text and me talking for a while. So what I thought I'd do for the rest of this is show you lots of pictures and talk about when 3D printing has been used in different applications for things. So when we're thinking about different applications, you've got a really wide range of where these parts are used. Now, apologies, these numbers are a couple of years out of date, but it's broadly speaking the same for now. By far the largest application of 3D printed parts is in end-use functional products. So it's moved from originally just as a prototyping modeling sort of process to the main use of these is the parts themselves are then used as the products or as part of products, as components. So we really care about the properties of those parts themselves. And if we think about things like functional prototypes, so it's still prototypes, but things where they need to have the right mechanical properties, that sector increases even more. We've also got things where they're used in the manufacture of other things, but not directly. So things like rapid tooling, where you can use 3D printing to make the tools or to help with the tooling. Also a big area, but they're things where the products still are used straight away. Obviously, it is still good for making models and prototypes and things like that, but it's moved away from that and it is mainly on these are the things we're going to use. So I say about different models. Got a nice example here. So this is an architectural model. This is certainly from the earlier days of 3D printing, one of the really great uses of it. So this is a full color print. It's made using binder jetting, so powder-based process, but it prints an ink onto it, so you can have a full color print. Now it's all very well, sort of showing people drawings of a house or like a 3D model you can spin around on the screen. But actually being able to print it out and show it to people makes a real difference. You can get much more of an understanding of how things work. So things like that are a really nice sort of introduction to everything. Similar sort of thing, and this is actually one of the things we've done at ManMet. I forget which course it was for, but there was a course where they wanted the students to be familiar with the anatomy of this particular skull. And if you've got a class with lots and lots of students in, well, you can't really hand around the actual skull just because of numbers, and there are probably ethical issues with that as well. So what we did instead, took a scan of the skull and printed out loads of replicas. So this means that you can have lots of the same thing. You can pass it around a class. If it gets damaged, broken, it doesn't matter. You can print out another one, and you can still get the feel for the exact shape and sort of move it around, manipulate it however the real one would actually act. So still using things for models, but in a slightly more applied sort of sense. Another thing that we've done at ManMet, so I don't know if anyone's been over and seen this. So the crucifixion, it's a big carved piece at Dunham Massey, really intricate, really big, really inaccessible, and of national importance, deemed by the National Trust. So they wanted to do something to preserve it. So what they did is they spent an inordinate amount of money having it professionally scanned. So there's a really high quality scan. Mainly they were thinking for sort of future repair work, so they've got something to compare it to and go back to. Then they got to the end of it, like, we've got this scan, can we do anything with it? So they approached us and we said, yes, yeah, of course, we can print out some of these things. So took some of these parts and printed them off. So if you go there now, so events, and I don't know if they're there all the time, but certainly for events, they have these on a table below. So you can see up close the sort of details of the carving. So this is really useful, but just to see it, but also think about if you can't see it very well from a distance, or if you can't see at all, it means that you can actually hands-on feel the shape of all of this without having to touch the priceless artwork and risk damaging it further. So a nice idea, lots of different applications for it, but again, still dealing with sort of models of different things. Okay, getting a bit more onto the practical side of things. So you have to indulge me, lots of these are laser sintering examples because that's my area. So I said about functional prototypes. So on the left, we've got an example of someone who's designing the case for a drill. And now this is ultimately going to be injection molded, but all of that area there, so all of that grey bit is laser sintered. So you can attach all the components in there. You can see all the insides in, the battery clips into it, and it still works as a drill. So you can test it, you can give it to people, handle it, say, how does it feel, all the rest of that, without worrying that it's going to fall apart and things at the end. Slightly different, but also things where it needs some mechanical properties. So there's a company there, I think this is for drones rather than for a full-size plane, but they wanted a model to go in a wind tunnel. So obviously it needed to accurately reflect the geometry, but still needed to put up with the force from the wind going through that tunnel. So they used laser sintering for that. For the black bits, I don't know if you can see on that screen, So like the nose and the wings and things. So they made a functional model to go in that particular application. I mentioned about sort of jewelry, lost wax casting, things like that. So two examples here. There's a nice octopus ring, which I think was cast in silver. I'm not sure, but I'm fairly sure that that would be either made with stereolithography initially, or maybe with binder jetting, so that they could then melt it out and make that mold around it. Then one of the writers laser sintered, so it's printed in polystyrene to make the mold of that mission. But examples of indirect tooling. So the final product isn't the printed thing, but it's used to make the thing that makes the final product. So it's slightly more indirect. We can go more direct. So this one on the left, if you think about, say, an injection molding mold, these have cooling in because you want to get quite a high turnout. It needs to cool down before you can eject the part from everything. And if you're making this conventionally, well, you've got certain restrictions. You want coolant to flow through it, but you can only drill a straight hole, which sounds quite obvious when you say it. But the fact that we can make holes which aren't straight are a major advantage. Because rather than just being restricted to, oh, we can fit a drill bit through there, we can actually take the coolant to where it's needed. So practically, that means that everything can cool down more evenly, so we don't have more internal stresses inside the parts. They can be quicker as well, so we have a higher throughput, and ultimately it makes it far more efficient because we can get more things through in the same time. And we've got things like jigs and fixtures printed around. So still using other machines, you can hold your workpiece in place consistently and sort of work through things that way. Lots of other uses for AM. Okay, getting on to the more end-use parts. So where you're actually using the parts as the final product themselves. So this is a really nice, but quite widely used example of how you can lightweight something with 3D printing. So this was a structural nose. I think it's for lighting in The Hague or something like that. And this was their original design, manufactured conventionally. And then they optimized it to various extents. And the final product they made was 75% lighter than the original one. So this is printed using SLM, so very similar process to laser sintering, but just for metals. And you can see it's a much more unusual shape that would be far more difficult to make conventionally. And you've got sort of examples which are more on the research side. I don't think this is used commercially. They dubbed it the world's lightest material. I'm sure I believe that either. But it is a fully metal lattice, which is light enough to be on the top of a dandelion. So you can do quite incredible things with it. I mentioned about part consolidation earlier. So this is an example from GE Aviation. This is their turboprop engine. And as it was, it had 855 different components. So think about all things bolted together, glued together, all the rest of it. They redesigned it for 3D printing, and they ended up with 12 components, which is quite a big difference. If you think about every single one of those joints of the original component as a potential source of failure, it's then a lot more reliable. They might have even been able to put more functionality in that they just couldn't before because they get different geometries that they didn't think about. So it makes it, even though the components themselves are more complex, it makes it easier to put together and deal with for things like that. I mentioned about scales of production. So laser sintering, I know it's laser sintering again, but it's quite good for different ranges as well. So it can go all the way from things like sort of custom cooling ducts. I think this is a cooling duct for a battery of some sort. So low volumes of production, single units or maybe low tens of units. Can scale up slightly more. So some of you might recognize this bike tool slightly. It was on Dragon's Den a few years ago. They actually used two different types of 3D printing. When they initially started out, they used this type, so like the cheaper FDM type for low levels and sort of initial prototyping. Then they moved up to laser sintering to make sort of the batch to mid-mass production sort of levels, about 400 units a month. And they used that for quite a long time. And eventually, when the company grew big enough, they then moved on to injection molding. So it was a really nice use case of going through different technologies that were appropriate at the time for the different scales. Then you have things that just work for mass production with 3D printing. So these are like very small wiring clips, and you can quite easily make 20,000 of them because you can have lots of them in the same build, and you can automate the post-processing to a certain extent and get high volume quite quickly. There are lots of medical applications. I'm not going to go through all of them, but here are some examples. So we've got some implants for things sort of internal. So we've got bone scaffold there to encourage bone growth. We've got a cranial implant there, also printed in polymers. Very common to also see these in metals, so printed titanium, things like that. You'll see quite a lot. I really like, and I want to see more of these arm casts, because if you've got like your arm in plaster, it's big, it's heavy, you can't get it wet, you can't reach somewhere to itch it. Whereas something like that, it's light, there's good airflow, so it doesn't smell. You can get it wet, you can reach your arm if it itches, but still has the mechanical properties needed to actually do its job. So similar to that, but a slightly bigger project, is something like the scoliosis brace that was designed over there. So scoliosis, so when someone has a curvature of the spine, you need to wear like a big bulky brace, which doesn't look very nice. It's painful to wear sometimes. People feel very self-conscious as well, especially for things like scoliosis, where I think most people that have it are sort of young teenage girls as well. So it makes quite a big difference in terms of image and self-confidence. Whereas if you could have something like this, which structurally does the right things, but it's almost like a fashion accessory, something you can be proud of. You can wear normal clothes over the top of it. Can be really good. And then seamlessly into fashion itself. Now, at the moment, this is sort of more reserved for high fashion and sort of one-offs, but it is something which potentially could become more mainstream. So this on the left was an example of a dress, and for thinking of how this works, think of basically chainmail. So all the individual pieces are rigid, but there are so many of them, they're all interlinked, that you can make something that acts like a material. It's quite fluid. So I've got like an example of one printed, different process, but it sort of acts like a material, but it's printed actually on this machine. Or you can fully embrace the fact that you've got solid components and just make weird things like that one on the right. Entirely what your style is and what you fancy. So yeah, sticking with fashion, this is actually a student project that we've got. And so we've just got in Print City a new printer, which is a material jetting printer, and can print on fabric directly. So probably much more accessible and applicable to everyday fashion. Whereas you can print not just sort of logos and all the rest of it, you can think about different materials, textures, 3D profiles, all the rest of it. And the question I get asked about this is, well, what about if you put it in the wash? Actually, this wash is better than most of the printed conventional materials. So it's not too bad on that. And we probably will see more of that in years to come, but it's still very early stages for things like that at the moment. And then changing track again completely. So thinking of big industrial projects. We've got concrete printers. We actually do some research on this at Man Met. And these are used, these are no longer just in labs. So there are entire communities printed, especially in sort of America, Mexico, of essentially low-cost housing, because it costs an awful lot less to make a house this way, because you don't have as much labor. Also, materials are less. You can see like the walls there are mainly hollow. Also means you get insulation straight away because you don't need to add that gap. And because it's automated, it's a lot quicker. So you can print an entire house in the span of, well, so less than 10 days rather than 2 months sort of thing. So we'll probably see a lot more of that going forward as well. Unlikely to come to Didsbury anytime soon, but you'll probably see more of it sort of around the place. Okay, so let's sort of start wrapping this up, thinking about some myths and things that people say to me about 3D printing. So people say you can print anything. There is no restrictions. You can print any geometry, anything like that. To which my answer is, well, sort of. We can print really complex things, and we don't have the same restrictions that we necessarily do with conventional manufacturing. But obviously, each machine still has its own restrictions, whether that's materials, whether it's feature size, whether it's tolerances. There is still a set of rules that we have to work with. Next one, and I hear this a lot, is you can print things which are impossible to make any other way. I'm yet to see something printed that is not possible to make any other way. Even if it takes someone months carving with like a tiny spatula or something like that, it is still possible to make it. What is sort of true on this is we can make things at scale which are not economically feasible to do conventionally. So we can mass produce things which are complex to make, whereas it wouldn't make sense to hire someone to sit in a shed and carve something for months if we were making 10,000 of them. So there is some truth to that, but yeah, there are still restrictions, and it's not the revolutionary miracle technology that we sometimes claim it is. This is an interesting one because this has changed over the last few years. Everyone will have a 3D printer in their homes. Now, I've spoken to quite a few of you. Quite a few of you do have a 3D printer in your homes. And especially in the run up to Christmas, you see them in supermarkets now. You see them like lots of deals on sort of Amazon, all the rest of it. I don't think, okay, so it might get to the point where everyone has one in their homes, but I don't think everyone will use them to their full potential. I mean, I don't really think it will get to everyone's homes, but lots of people will buy it maybe as a novelty. Some people will use it to its full potential. So hobbyists, engineers, maybe if you're trying to show it off to kids, show them science, engineering, things like that. But I don't think it's going to be something which we definitely see in everyone's home at some point in the future. And I don't think it will ever get to the point where everyone has it in their home as a major component. I think it's always going to be quite a specific niche thing to have. So is 3D printing the future of manufacturing? Well, it's not just going to be a simple yes, no answer. 3D printing definitely has a place in the future of manufacturing. But there are definitely processes where it is better to use the conventional methods than the new 3D printing methods. So yes, it will replace some things, and you will definitely start to see more 3D printed things around you. Might see like bits of the Christmas market when I wander around. There are bits in cars that are now 3D printed. So you will start seeing more of these, but it's not going to take over the world. It's not going to be the one thing that we use for everything. And we are a long way from having the Star Trek replicator, which is what a lot of people think when they think 3D printing is that's what we're going to get. That is a very long way off. We have some really amazing bits of kit, but it's not quite at that level. So I think I will leave it there. I'm going to hang around for a while. Feel free to come up. I'll set this off again. Have a look at all the bits that I bought. Come chat about 3D printing. Feel free to get in touch. And are there any questions? Well, yep. So that's an interesting one. There are a few different ways to do that. Generally, they are material extrusion type processes. So similar to this sort of machine, but it doesn't go through a heated nozzle. It basically just imagine a syringe on a set of axes. So you can have it depositing it on 2D substrate maybe, or there are some which have basically a block of gel where the needle of the syringe moves around and it just deposits things as it's moving. So it's sort of 3D, but suspended in something else. So again, new technology, we'll get there. We're not at the point of printing organs. That's another thing which I should have put up there. We can print tissue. That's something we can get to, but not fully functioning organs as of yet. Yeah, so my research, so I work with laser sintering, as I mentioned, and sort of adding functionality. So I've been developing materials that when they come out of the machine without any more post-processing are antimicrobial. So things like bacteria don't grow on them, and sort of it can kill bacteria that comes into contact with it. So that's sort of more my research area. So yeah, on the material side of that. Yes. So there are lots of different materials that you can print. Things like melting points for polymers, that will make a big difference. This machine can only go up to a certain temperature. If you have a much higher temperature, it probably needs to be in a heated build chamber. If you want to print really high melting point materials, the cost just keeps on going up and up because you need to have components that work at those high temperatures as well. For metals, that's a lot of the reason why They're quite expensive. You need really high temperatures to melt metals. Also loads of other health and safety problems and things with that. But yes, it does make a huge difference. But for these sort of printers, definitely the ones that they'll be selling in the middle aisle at Aldi and sort of that I'll bring around, they will pretty much only print PLA. So you don't need to worry about the different types of materials, mainly because PLA works well. It's not it's renewable. It's made from corn, I think. So technically, it is biodegradable and renewable, and there's no problem breathing in fumes and things like that. So for most of the printers that you'll interact with, you don't need to worry about melting points because it's all the same material. Yeah. Mhm. Yep. So, I mean, I'll happily come back and talk about my research another time. The way that I've done it is I've put additional additives into the parts. So I've put silver-containing additives in, and silver, if you're not aware, is a really strong antimicrobial, works in lots of different ways, been used for about 3,000 years for its antimicrobial properties. So the parts that I make, if they're in contact with water, through the nature of the polymer, it will absorb water and sort of give out silver ions to kill any bacteria that come into contact or in the surrounding areas. But there are lots of different ways of making antimicrobial material. That's just one of them that I've looked into for this.
It's just a question I'm relaying from the audience online. Can you assure the strength of the product compared with conventional?
Oh, that's a big question. And it very much depends on what conventional method, what material, and what printing process. There's a lot of ifs and buts and things. So for things like these ones, so like a nylon 12 printed with laser sintering, the ultimate tensile strength of these is about the same as for injection molded. What isn't as good is the elongation at break. So they will snap at a much shorter extension than conventional ones. But this is still pretty good for all of these. There are some processes. So for example, if you're working with metals, you can get properties which are equivalent to wrought sort of properties. So actually really strong parts. And in some cases, you can get them to be stronger than conventionally manufactured parts. Yeah, so it very much depends on the process and the application. But yes, you're right. Some of them, the properties are a lot less than conventional methods. But generally, especially when we're talking about end-use products, they are as good, if not better in some cases.
Applications in medical spaces and 3D printing is really cool. But like, what are the barriers to adoption? Why are we seeing it more?
So that's an interesting question. So there are a few different reasons. Initially, a lot of it was around legislation. So I mentioned about standards and quality control and all the rest of it. There are so many things that go into a 3D printed part that you need to track every single aspect of that process. So say you're making a metal implant for, say, like a cranial implant. There are standards now in place that will track how the powder is made, where it's made, what processes it's gone through, when it was printed, how it was printed, parameters for that, how it then got from there to the hospital and all of that. But it took time to get all of those sort of legislations in place. And then if I come out and say, oh, I've got a new technology, basically, they'll have to do that all again. So it does work, and it is quite widely used in medical at the moment just for specific applications. We've got past the point where we don't need individual approval for individual parts because there is enough of a process in place that we can just say we've followed these standards. And it is fairly regularly used, just depends where in the country as well, or where in the world it is. Some hospitals in, say, like America, we use this an awful lot more because money is a lot more freely available over there. So you can spend a lot more and justify all the use of this. But yeah, it is definitely used in medical, even if not for direct applications. So there are far fewer rules around medical devices, for example, for different classes of medical devices, but certainly external contacting ones, these are quite widely used. So I mentioned about like the arm casts, braces, things like that. Skin contacting things quite widely used. One of the early uses of 3D printing was for burn masks. So that was a really a good example of the traditional way to make a burn mask is basically to get some putty and to mold it to someone's face, which you can imagine if you've got like a big facial burn isn't very nice. It's quite painful and quite traumatic. But with this, we can simply take a scan, so no contact to the person, and print out something that is that exact shape. So we know it will fit without actually having to press things into the wound before. So there are lots of different medical applications, things like surgical guides and things like that, which are quite commonly used.
Yeah, I have a question about intellectual property. Is it easier to protect designs if they are 3D printed, and is it harder to reverse engineer things in that perspective? Does that make it attractive or sort of the opposite?
So I think it's a lot more difficult to say copyright a design or protect a design if you have it in a file, because there are different people looking into this. But if you have a file and then someone gets hold of that, they can print that exact thing on their other printer somewhere else. There's nothing stopping them then selling that thing and making a profit. But who does that go to? Is that yours? Is that theirs? They're the ones that printed it. It's your design. So it's more complicated with things like that. In terms of reverse engineering, it's probably as complicated as any other process would be. Realistically, probably scan it and then work backwards from there. So unless it's a really complex geometry, you can probably work it out. But yeah, finding ways of sort of watermarking prints or protecting it, verifying their origin is a really big area that people are looking into now, and there's not a simple solution for it. Yeah.
Sort of working at the industrial scale, we have sort of engineering 3D printing houses that will make anything with engineers that take it from beginning to end, or are specific companies buying their own machines, making things, or is it a mixture of both? Because you seem to be straddling as well, sort of academia and manufacturing as well. So I'm just wondering how it all works and where is it now, where can it be?
Yep, so there are a few different business models for 3D printing. So you can have the in-house manufacture. So you buy your own 3D printer, you use it and make parts that way. You can, or if you're sort of earlier on, don't want to commit to it, you're not quite sure, there are lots of different service bureaus out there. So basically you can send them your design or work with them on making your design. They will print it and send it to you, basically. So that's also a thing. So like hospitals, when they're looking to put this technology in, they'll often start with an external print bureau. So they can test a few things first, and then they're more informed for making a decision of whether to buy it at the end. Sorry, what was that? Yes, yeah, a 3D printing service or a company that basically has 3D printers and will print things for you.
You're in that role.
Sort of. It depends on the company you go to. No, very good question. So these type of printers, so all of these designs came from the RepRap project, which is basically a project for 3D printers printing 3D printers. So if you come and have a look at this later on, all of the orange parts and all of the black parts on this printer are printed on the same type of printers. So there is, these ones are from, printers are from the Czech Republic, I think. And there is basically a massive warehouse with hundreds of printers printing printers. And that's the way that their business works. Take over the world. It's not a point to take. There are still other parts on this. You can't print everything. But there are components of it that you can. And yeah, that was the whole idea of that project, of making it so you can print as much of it as possible.
Speaking of taking over the world, I've heard of medicines being 3D printed.
Yes.
Talk to me more about that.
Yep, so that's definitely possible. So there are, okay, so let's think about the reasons why you might want to do it.
Yeah, that's what
So it could be that you want a certain combination of drugs in a certain ratio, for example, or you might want to change the geometry or makeup of the drugs themselves to have a different, say, release rate or dissolve at a different rate, so you want certain geometries. So there are different ways of doing that. Machines like this one, or similar to this one, similar to what we were talking about, the bioprinting, to basically squeeze out a paste and it sort of dries that way in that sort of shape. with sort of my own area of laser sintering. You can start with powders and spread layers of powders so as an example I saw of someone had printed something which was 50-50 of paracetamol and ibuprofen. They started with powders, they could melt them with a laser, so they processed it using laser sintering. So you can think about the custom ratio, the custom release rates and things like that with those sort of processes. So yeah, definitely used and can be used more in the future. Similar answer to why you do 3D print food, because there's lots of 3D printed food going around now. The more common ones are things like printing chocolate, which is basically the same sort of technology as this. Also weirder ones where they 3D print meat, not actual meat, things grown from meat and meat substitutes, things like that. So yeah, it's a weird sort of world when you get to that point, but yeah, certainly areas where 3D printing can be used.
How biodegradable is this? Looking at your table now.
Mhm.
How degradable is that?
So I've got a range of things in different materials on here, some more biodegradable than others. I can't give you in terms of how many years it will last before it will biodegrade. The ones that you brought in, like these ones, it is all in PLA, so they are from a natural product and they will biodegrade without any negative effects to the environment. So it might take a long time, but there aren't any nasty chemicals that would come out at the end. Others will probably last longer. Oh yes, but it's nowhere near that sort of level. We're talking about so like with the 3D printed meat, it's basically like a paste that you can print in a certain pattern. You're still restricted to that paste that goes in. You can't. It's like with a replicator, like print a martini, for example, because you need lots of different ingredients somehow. But yeah, there's a long way off it. No, it doesn't. It's also insanely expensive. Any more? Is that a question?
No.
Oh no. Yeah. Yeah.
You mentioned system constraints, and we've heard a lot about the small ends.
Mhm.
What about the large ends? I mean, I was looking at the Elgin marbles, and I thought,
Mhm.
can you do a statue of a human size?
Yes, is the answer to that. There will just be different constraints with that. So if you, it also depends on what material you want to make it out of. So that those concrete printers that I was saying about, we're fairly near the end of this. So you can see that they are obviously massive size, but the layer lines are huge. So we're talking about sort of like that for layers, and you can sort of see on the edge of the house, you've got that texture there. You might want to sort of plaster over it or something like that, but as printed, you have those very distinctive layer lines. So in those sort of materials, yes, but it won't really look like the original. You can have really large resin prints. So I've seen a 3D printed kayak, which is sort of all very smooth and comes from like the stereolithography type things. Because it comes from a vat, it's quite surreal. Sort of on the floor, they almost draw a canoe out of the thin air beneath you. So you can do that, just it depends on the size of your build chamber in that particular instance. For things like this type of printing, you can mount the nozzle for this on basically a robotic arm. So you can print things the reach of your robotic arm. You can have like conveyor belts going away from it, so you can print really long things. It's usually a trade-off between accuracy and size. Not always, but usually it is. Because if you want really detailed things at a large size, it will just take a very, very long time and be very expensive.
So on that printer, James, my kids are asking me what I want for Christmas. How much would one of those cost?
This one is a Prusa Mini. I think it's about 500-600 quid, something like that. The thing I really like about Prusa, and I'm not selling Prusa, I say about the printers printing printers. These are all like official components for things. Lots of them are sort of cheap Chinese knockoffs, which don't work for very long. If you were to make this from scratch yourself, it basically costs the same amount of money. So the filament for this, if you buy their official one, I think it's about £15 a kilo or something like that, maybe a bit more, maybe about £20 a kilo. You can find cheaper ones. But But yeah, the nice stuff is sort of, yeah, 20, 25 pounds. So,
Anyone else got
Ooh.
questions for James?
in which case, yeah, I'm going to stick around. Feel free to come up, have a look through printed parts, ask more questions.